Okay, good afternoon, everybody. Welcome to the first in what we hope is an exciting series of virtual webinars that we'll be hosting in the coming weeks. The first of which is looking at network segmentation with EVPN, looking at VXLAN and MPLS transports. Now, for those of you that are new to the Zoom software, you will see there is a Q&A tab to ask a question and answer. So what we'd recommend is if you do have any questions during the presentation, feel free to ask them in the Q&A, and we have a team of panelists ready to answer those questions for you. So looking at the agenda we have for you today, we're going to give a brief introduction to network segmentation, and then look into a technology known as EVPN, looking at the fundamentals of that technology, both layer 2 and layer 3 VPNs, and we'll showcase that with some live demonstrations and touch upon multicast for EVPN as well. We'll then look at some of the various design options we have in there, maybe some new acronyms to you in there, such as IRB, integrated routing and bridging, multi-homing, load balancing, and so on. We'll then look at some multi-tenancy design examples and use cases, whether that's for enterprises or service provider customers, and then look at some transport choices, VXLAN versus MPLS, and some of these newer technologies such as segment routing and comparing that to existing technologies. So with that, let's look briefly at an introduction to network segmentation. So really, what do we mean by segmentation? Well, it is at its simplest level. If we look it up in the dictionary, we can see it's defined as the division of something into smaller parts. So what does that mean when we actually look at our networking infrastructure? Well, we can actually segment our networking infrastructure. We might want to do this for a number of reasons. That could be multi-tenancy, it could be security isolation, it could be compliance assurance, for example. And how are we actually going to segment this networking infrastructure? Well, actually, this is something that has been around in one form or another for decades, right? This could be something as simple as VLANs to segment our infrastructure. And naturally, as you can imagine, this could also be more complex technology. So if that's what segmentation is, why might we be wanting to do this? Well, I think one attractive benefit is the efficiency of our infrastructure. If we have an investment in physical networking assets, then segmentation allows us to share those physical assets, whether that is for multi-tenancy, and those tenants could be internal tenants within your business. For those of you who are service providers, obviously they could be customers. But other reasons we might want to do this is also for security isolation. Those of you who do credit card payment processing, for example, will know the importance of ensuring compliance of that data, and segmenting our network can help with that. Another benefit really of using the newer technologies that you'll be seeing today is you're really getting access to what are service provider grade technologies, but you can actually run them on what you might consider data center level devices. So we're actually taking the power of that merchant silicon that has proved such a success, and we can use that with these modern segmentation technologies. Fundamentally, we're doing more with less, right? We're taking that finite amount of physical asset and dividing that and really making the use of that. So if you want to call it cloud principles, that's really what we're adopting here, right? We're taking a number of the lessons of the larger cloud providers and making those benefits available. So that's what we're seeing at a high level. And I'd now like to hand over to one of our systems engineers, Alexei, who's going to talk about the fundamentals of this technology.
Thanks, Dave. I'll start with the EVPN fundamentals for covering the use case of segmentation. So segmentation is a high-level requirement, and that's being delivered through different services, whether it's ELAN, E-line, there's pseudo wires, L3 VPN, locally you would have VRFs and multi-tenancy. And all these services will be delivered by EVPN as a new single overlay technology that will be capable of supporting all those different services to the end goal of segmentation. So what is EVPN? This is a control plane protocol that will deliver all these services we mentioned, both at layer 2 and layer 3. Traditionally, those services were provided through different technologies, protocols, while here VPN is providing consistent and a large amount of services through a single protocol. So the advantage over the traditional VPN solutions, Dave mentioned segmentation and VPN already existed, but the advantage of EVPN is that simplicity of implementation and design and the flexibility of the services is going to provide. It's based on BGP, so many of you hopefully like BGP. It's very scalable, it provides a lot of granularity, and it supports many different protocols. So it's very well established, it's a very robust protocol, it's got it's very well established, meaning you've got expertise in the design, in the implementation and troubleshooting. It provides, compared to the traditional layer 2 services, advantages such as there's no flooding. The traditional VPLS, for example, as a ELAN, was based on data plane flood and learn, meaning that there was no control on the distribution of the MAC addresses. But here there is no flooding, and also it's possible to control the propagation of the MAC addresses because it's BGP prefixes, or it's BGP routes that will carry the MAC addresses. It's possible to filter them to control through import and export of route targets, or apply filtering on the BGP session. And therefore, with all these advantages, the EVPN solution for layer 2 will scale much better. We mentioned before it's a single control plane for both the layer 2 and the layer 3 VPN, as opposed to having a collection of different protocol and solutions patched together. And when looking at the ELAN solutions, or L2 VPN, you are very flexible in the topology, in the sense that you're not restricted to one to many or one to one, for example. So wires, you can have any to any. So you've got a single design for your point-to-point or point-to-multi-point, as opposed to having a requirement for multiple layer 2 solutions. And finally, VPN provides the active-active layer 2 multipathing, as opposed to the traditional technologies using only active-passive. We mentioned it's a new protocol. It's a new protocol for VXLAN, for example. But actually, EVPN has existed for MPLS under the RFC 7432 for a little while. It uses the BGP control plane with a multi-protocol BGP. There's a new address family. It's providing L2 VPN and L3 VPN under that EVPN address family. And so through a single protocol peering, so through a single EVPN BGP peering, you'll be able to carry on that single exchange all the different routes for carrying the MAC addresses and the IP prefixes for the L3 VPN. One of the advantages of EVPN is that that dissociation between the control plane and the data plane. It relied on 7432, the RFC of defining EVPN for the MPLS data plane. However, with the new RFC 8365, it's now possible to use that EVPN control plane with additional forwarding plane, such as VXLAN, for example. So you've got that control plane, EVPN, and MPLS is one data plane, but you can have VXLAN as a data plane. And my colleague Sean is going to talk later on when you choose one over the other. So the new address family on the BGP allows the exchange of EVPN routes through the address family AFI 25 and the subaddress family 70. There is the technology, the EVPN standard, make use of well-known constructs such as the route target that allows the import and export of of routes across VPNs, whether it's L2 VPN or L3 VPN, as well as the route distinguisher, the RD, for identifying clearly the origin of the route advertisement and to prevent overlapping, and to provide overlapping address spaces if needed. So let's look at the different route types that are now advertised by EVPN. We can see here route 5. The route type 1 and 4 are used for multi-homing, and Sean is going to detail that. So what we'll focus on first is the route type 2 that's used for distributing the MAC addresses that will be used for the layer 2 VPN or different layer 2 services. The route type 3 is called an IMET, Inclusive Multicast Ethernet Tag. So that's used for distributing the EVPN, in EVPN, the VNI to VLAN membership. So when you want to someone at PE wants to advertise interest in receiving some broadcast or unknown unicast multicast, is going to send an IMET in order for the remote PEs to send that PUM traffic, PUM traffic to that PE. And one thing to mention on the MAC address is that it's called route type 2. It can advertise MAC addresses only, but can optionally advertise IP addresses as well. So it will be a MAC plus IP. And finally, skipping 4 because that's for multi-homing, the route type 5 is used for IP prefixes. So that's going to advertise a subnet, a prefix length. It doesn't advertise at all any MAC addresses. So that's purely for the L3 VPN. Going in a bit more details on the L2 VPN use case for EVPN, I wanted to compare it a bit with some traditional technologies, ELAN and ELINE based on MPLS. So you had flood and learn in the data plane, meaning you had an Ethernet frame that was flooded to all the recipients, and the MAC addresses were learned through the data plane doing MAC address learning. Now with EVPN, there is no need for flood and learn in the data plane. It's possible, we do a learning locally, but then the MAC addresses are distributed through BGP. So BGP is used here with what we've seen in route type 2 to carry the MAC addresses assigned to a specific L2 VPN with the route target and the route distinguishers. Then the encapsulation on the data plane can be either MPLS or VXLAN, meaning that the data plane will do a tunneling encapsulation to the remote PEs. And on the origin PEs, there could be several PEs. The EVPN technology supports active-active. So some example of L2 VPN services is, for example, ELAN. You might know the MPLS equivalent as being VPLS, whether it's LDP or BGP signal, but that would be EVPN based, ELAN service, L2 VPN with the VPN protocol. Distributing the MAC only. There's also the ELINE service providing the solo wire functionality with no MAC learning. What I'd like the audience to think about is which one of these in the route types we've already seen. It's just this kind of little quiz. We'll just try to have a little brain challenge early in the morning. Sorry. These route types, we've discussed about them. Could you recall which one would be used for the L2 VPN service? So the L2 VPN is L2. We need to distribute MAC addresses, so you can already guess what we're going to use. There's a little bit of a trick here. And if you thought about it, did you include the route type 3 for that? So the IMET is important for the layer 2 VPNs because MAC addresses are obviously advertising MAC addresses. They are known MAC addresses and they are known destinations. But what about in case of broadcast or unknown unicast? So when there's a MAC address, that MAC address is not in the table, so we don't know where to send it to. So the IMET is important because it's going from a PE that participates into a given broadcast domain, a layer 2 segment, advertised to all the remote VTEPs or PEs that it wants to receive any broadcast, unknown unicast or multicast traffic, BUM traffic in that particular broadcast domain. So there will be a VNI. a P assigns a VLAN to a VNI, and all the remote Ps should therefore send that bump traffic to that P because the destination might well be behind that. So the IMET is an integral part of the L2 VPN. That membership advertisement is critical for the ARPs and all the multicast and non-unicast. And here is a CLI output. So I'm going a little bit technical with CLI, not to scare people or not to go, we do go, it's a technical presentation, right? It's not just slideware. The goal is just to have a diverse view of the technology we're talking about with more concrete examples. So here, this output illustrates an EVPN table, BGP EVPN table. So that's the list of all the different routes that we've received by EVPN, and there are several of them. So can you try to spot which one will be the route type 2 in that output? Again, mini quiz. We're here to learn. So I'd like you to spot which one are the route type 2. Route type 2, that's for distributing the MAC addresses. So maybe you can already figure out that maybe the keyword MAC. Maybe you can recognize the MAC address in these. And what I wanted to highlight here is the fact that despite talking about route type 1, 2, 3, 4, 5, there's also a little name for each of these route types. So for example, the route type 2 is called the MAC IP. It mainly distributes MAC, but it can distribute the IP address mapping for that MAC as well. So it's called a MAC IP. The route type 3 is called an IMET, and the route type 5 is called an MP prefix. So that was the purpose of that small little exercise here. Spotting being used to the names and being used to spot them in an output. So it was that MAC IP. We've got two of them. We've got one that's MAC only, and the other one that's MAC plus IP. The MAC only is mandatory. The MAC plus IP is optional. It could be used for up resolution. Likewise, where's the route type 3? I went through it, but route type 3 is used for advertising the membership, and that's this IMET here. So what we advertise the source VTEP, and we advertise also a membership to a specific VNI. Before I continue on the layer 3 VPN, I wonder whether there's any question, Dave, to answer?
Yes, Alexi. So one question we had from your previous slide, where it showcased only 5 route types. The question is, are there more than 5 route types?
So yeah, the protocols is the standard are developing, and there are more route types used, for example, for the multicast EVPN. So that's also possible. We're going to cover that a bit later, but yes. And 1 and 4 are going to be covered for the multi-homing by Sean. But yes, they are more. And the protocol is flexible. So in terms of EVPN for the layer 3, what it compares with the traditional way of providing multi-tenancy in the layer 3 routing was to establish a different VRF Lite instance to establish different peering per VRF Lite instance, whether it's an IGP, could be BGP, but it doesn't scale because you need to preserve that peering for each individual VRF. And as you want to preserve that segmentation across all your network, then you will need to have the same peering all the way in a chain all over the network, which doesn't scale at all. So then there's the RFC 4364, which is the IPVPN for MPLS, that provides a single BGP session to carry all the different VRF VPN information across the MPLS network. Then we go on to the EVPN implementation of that layer 3 VPN service. As we discussed before, that same EVPN service that's going to deliver that same EVPN protocol that's going to deliver these layer 3 VPNs services, is the same instance, the same peering that will also carry the layer 2 services. So across that layer 3, I can carry multiple VPN information, so I can have different tenants, routing table, segmented and carried across the network with choice of MPLS or VXLAN transport. So now let's go to a little quiz again. What would be used as a route type for providing the L3 VPN service? So L3 means route prefixes, so it's fairly easy, but you would have spotted that it's an IP prefix. Do I need anything else? Maybe that's a question. Do I need MAC addresses? Because the IP prefixes don't carry any MAC address information. Do I need the IMET? No, only the IP prefix is needed. There is no need for broadcast or resolving that VNI membership to VLAN, because we focus here really on the layer 3. And again, in my output, we're going to see that in a bit more detail, but where is the route type 5? The route type 5, look at the names. It's not just route type 5, it doesn't show as route type 5. The standard name is IP prefix. So we've covered, with some slides, explanation, introduction about EVPN, the layer 2, layer 3 services. And what I'd like to go is go a bit deeper and provide an example with a demo of how the traffic goes from a host, which is a VTEP or a PE, and across the spine, which is the remote end. So we're going to look again at those route types and understand how EVPN works, both for layer 2 and layer 3, for providing segmentation in the network. So both the layer 2 provides multi-tenancy and layer 3 as well. So I'm going to jump into the live demo using those diagrams as a base. What you've got here on your screen is the physical topology is illustrated here. We've got two spines. I've got a leaf. I've got the leaf 1 here. That's my VTEP/PE that connects to some hosts. And on the remote end, I've got leaf 3 with some hosts as well. And the logical topology on the right-hand side is that I'm going to carry the traffic from those hosts on the leaf 1, and the traffic is going to be mapped to a VXLAN tunnel. So I'm using VXLAN as transport. EVPN is going to distribute the reachability, whether it's layer 2 as MAC address or the IP prefixes. So I'm going to run through different use cases. One is layer 2 VPN, and then afterwards I'm going to do L3 VPN. So what we've got on the left-hand side, I've got my leaf 1, and I'm not sending any traffic at the moment. So if I do a show MAC address table, I've got an empty, well, what's that? I've got no locally learned MAC address because my device is not sending anything. So if I do a show BGP EVPN, sorry, I was on my L3 VPN demo. So I wanted to start with the L2 VPN. So show MAC address and the table, I've got no MAC address at all because I'm not sending any traffic from host 1 yet. However, as soon as I have configured a mapping between my VLAN, here for example I've got VLAN 12, and do a mapping to my VNI 1200. For reference, the VLAN numbers and the VNIs are here on the right-hand side. Then, as soon as I've got that, the switch needs to inform the remote piece that it wants to receive the bump traffic. So that's being done by the route type 3, which is an IMET. So here you see my different advertisements of the IMET, route type 3 by VPN. They are locally originated, and I've got one for the VLAN 12, one for the VLAN 34. Let's look at one of them in detail. You don't need to be scared about all the CLI, right? The point is to show you exactly what we talked about with a practical example, so that you can follow exactly what we already saw as an individual route types, but in the case of a complete end-to-end story about data plane and also control plane distribution across the network. So my route type 3 here, the IMET, coming from this locally originating PE, has got a route target. The route target will allow to identify these prefixes, and therefore the remote PE will be able to import either with in a blanket manner everything, if everything has got the same route target, but it can be granular. So that's another story for building segmentation with more granular policies even within a single L2 VPN. And then we've got a VNI assignment for the data plane, which means if anything is due for that VNI 1200, please send it to me. That's what will happen with broadcast. So as I mentioned, we've got no MAC address entry. And when I'm going to ping here from my host 1, I'm going to ping my host 3 on the right-hand side. What's going to happen first is, because host 1 doesn't have the MAC address, so it's going to send an ARP entry to, an ARP request, sorry, to leaf 1. That will then broadcast that to whoever remote P is interested in that VNI. So when we looked at the EVPN table, that is what I was originating locally. But you can notice that I received some IMETs as well from leaf 3. I received 2 of them because leaf 3 has got dual connection to the spine. There is equal cost multipathing at on that EVPN peering. And therefore, I receive the route twice, which is perfect. It's what I want, because I want to do multipathing in an active-active manner. So I've got these for the VLAN 12. I receive them. I know that leaf 3 is interested in the BAM traffic coming from VLAN 12, and therefore I'm going to send the ARP request to leaf 3. While at the same time, the leaf 1 is going to do local MAC learning, and as soon as I see an Ethernet frame from host 1, I'm going to populate my MAC address table. And as soon as I got a MAC address table on the VLAN 12, I'm going to advertise a route type 2. So currently we don't have all that, but that's what we should see right now. So I'm going to ping my host 3 with 100% success. So let's look at now what we've got in the address table. In the address table, I've got that MAC address locally learned from Ethernet 4, and I'm going to confirm that the MAC address is indeed correct, ending in E8B5. So show interface VLAN 12 here. I confirm that this is my my host 1 that's been sending traffic with that MAC address, and the leaf 1 has put it into the MAC address table. So what do we expect now into the BGP EVPN table? We are seeing a route type 2, spot the MAC IP here. That's with this MAC address, as expected, ending in E8B5. And in the diagram, that's going to send that across to the spine. That's going to be distributed, whether the spine are doing or just devices in transit or route reflectors. That's going to be received by leaf 3. Let's confirm that leaf 3 has got that. Show BGP EVPN. We've got indeed the 2 route type 2 from leaf 1, 2 paths as expected, and whether it has installed that locally on its local MAC address table. And we can see that leaf 3 has installed the MAC address ending in E8B5 into its local MAC address table, and the port where it learned it from is VXLAN 1. When leaf 1 receives a response from host 3, is going to know where to send it to, because it's behind VXLAN 1. I've got interface VXLAN 1 here where I do the mapping between, I see the mapping between VLAN 12 and VNI 1200. And I know that when I need to send traffic, if I've got any BAM traffic, I can send it to that specific VTEP. So now, when Leaf1 sends the traffic back, sorry, when a host 3 responds, Leaf3 knows where to send the traffic to Leaf1. It's in the MAC address, it's in the EVPN, so I know where to find it behind Leaf1. And that's why on Leaf1, you see also in the MAC address table, the host 3 MAC address. And that's the case for, we've just seen end-to-end communication. We've just explained the control plane, how the MAC address is being distributed from Leaf1 to Leaf3. And when host 3 responds to the ARP request, and thereafter the ICMP request, Leaf3 is going to encapsulate the traffic to the correct VTEP 1. And VTEP 1 is also going to receive from Leaf3 a route type 2 with the MAC address of host 3. And we've just gone through the data plane and the control plane walk through. One other thing I'd like to do is illustrate multi-tenancy with overlapping MAC addresses in this environment. So I've pinged a host in the VLAN 12, now in the VLAN 34 additionally. And what it makes is that in my EVPN table, I'm advertising the MAC addresses, not just, here is my MAC address in the VLAN 12, and also now in the VLAN 34. So that's the same MAC address. So what I wanted to illustrate here is the multi-tenancy. We support MAC address overlap, but the segmentation is preserved because each is in its own L2 VPN, and that separation is preserved all the way through the whole network. One other thing I wanted to detail on the MAC IP, you can see here that they are only the MAC only route type 2 MAC IPs. What I'm going to do, I'm going to force a ping to the default gateway because we were doing just a pure layer 2 transmission here within the same subnet. We stretch the layer 2 segment across my layer 3 network with VXLAN, but we haven't requested anything to the default gateway. So I'm just going to ping the default gateway here successfully. So what I will now have is a MAC plus IP. So that's what I wanted to show you, that how it looks like when there is the MAC plus IP. And I've got an additional something to show you with the MAC plus IP when we've got both the MAC and the IP that's related to the ARP entries. So let's look at the ARP entries. I've just done a flush here, so it has gone away. Show PGP EVPN. Again, I did a flush for everything. So the MAC plus IP has gone away. I'd like to show you now another ping for the ARP, because I've assigned also that ARP to a VRF. So when an ARP entry is assigned to a VRF, what we can do for that MAC plus IP is assign that VRF information so that the remote end is going to receive that route type 2 with MAC plus IP, meaning Leaf3. When Leaf3 is going to receive that route type 2, it's got the MAC address, it's got the IP address that is part of the resolution, the ARP resolution, and also the VRF. So Leaf3 is going to be able to assign that ARP entry into a specific VRF. So what it looks like on the on Leaf1, that's going to advertise that. I'm going to say route type MAC IP plus a specific MAC, and I'm going to look into the details into my MAC plus IP. So as opposed to the MAC only route type 2, where I've got only the MAC only, and they only have the route target for the layer 2, for the VLAN, and the VNI that's mapping the VLAN data plane into the transport that's going to encapsulate into the VNI all the layer 2 traffic. So my MAC plus IP is slightly different. It's got the IP address here, and also you notice in the route target, we've got a slightly different additional root target that's related to the VRF. We've got my L2 VLAN here, VNI, and here I've got my L3 VNI, which means that on the remote end, on L3, when I receive all that information, I receive a root type 2 with MAC plus IP. It's not just in the default routing table, and I don't know what to do with it. I can put it into a VRF, and I can act as a proxy ARP. I can install proxy ARP entries to avoid the ARP request from host 3, for example, from going all the way across the network and then coming back. I can respond to the ARP request locally. So let's look at what we've got for the ARP entries. Show VRF, show ARP, sorry, VRF A. So I've got my IP address on host 1. You can see the IP address is here on the diagram. I've got my MAC address ending in E8B5 on VLAN 12, so correct, and learned by VXLAN. And if I do a flush of that, that ARP entry for that VLAN, then it will propagate the change, it will flush it as well on the EVPN. So the ARP distribution is now part of the EVPN control plane as well. Let's do a clear ARP RFA for that specific IP. I can see that, yeah, I can see that it disappeared from the ARP entry, from the ARP table on leaf 3, and should have disappeared as well from my local EVPN table. So you can see that there's no more root type 2 MAC plus IP. That was the EVPN demonstration. What we've demonstrated is control plane distribution of the MAC addresses, data plane end-to-end between host 1 and host 3, the segmentation of these layer 2 by preserving the multi-tenancy, even if when they are conflicting or overlapping of addresses all the way but locally, but distributing that across the whole network. And we've seen the distribution of the ARP information to provide the proxy ARP functionality onto the remote PEs to optimize the traffic flows. And now what we're going to see is with the same physical topology, we've got a slightly different lab instead of layer 2, that's layer 3. So in this use case, what we've got is a tenant that's got some subnet distributed across the network. For example, is got on host 1 here, I've got, short int brief, I'll show you my different subnet. I've got my active subnet that's 172.16 and it's ending in 115.100. While on host 3, I've got 116.100. So these subnets are separated. They are, there's isolation. And I'm going to provide end-to-end layer 3 communication by distributing that prefix information across the network through the L3 network by EVPN and my root type 5, the IP prefixes. So if I do a show BGP EVPN, I'm not distributing any MAC addresses anymore in that lab. What I'm doing is here I am leaf1 in this on the left hand side. I'm advertising my /24. That's the 115.100 host. So my subnet is 115.0. That's my local subnet that I am advertising. I'm also advertising my loopback. So leaf1 has got that loopback as well. I am receiving from leaf3 through 2 path, again, ECMP. What I'm receiving is the 116 subnet. So leaf3 is advertising its local subnet where it's got host 3 across the network till leaf1. And I'm going to test that. So I'm going to ping, I am on 115.100 and I'm going to ping 116.100 across the layer 3 network. It was successful. I can confirm that in the control plane. I'm on leaf 3, show IP root. All the roots in that instance, in that tenant routing table. I've got my local 116.0 here. That's for leaf 3. And also have learned the 115.0 that's in my routing table. I've received it by BGP. It's in my EVPN table. That's a root type 5. And it has been installed in a routing table, and the connection is via the VTEP 111, and the VNI is that single VNI for that tenant that carries all the IP prefix reachability information. So that concludes the demonstration. In addition to the layer 2 multi-tenancy demos that we had, we have now shown a tenant that has got multiple subnets, and that tenant was able to do routing from a subnet, from an isolated subnet, to its default gateway, leaf 1, sorry, from host 1 to leaf 1. Leaf 1 had the routing information to reach the remote subnet by having learned it through EVPN and its root type 5 distribution. And you can have multiple tenants, you can have multiple L3 VPN, having routing between all these subnets wherever they are located. And Sean will discuss later about the design. First of all, how do you work out? What's the best way to design that? How does that work between tenants also for north to south traffic? So that concludes the demo, and I'm coming back to the presentation. Dave, is there any question following that demo or anything else I've talked so far?
Yes, thank you, Alexei. We've been having many questions, most of which we are doing our best to answer in the Q&A tab on Zoom. And so if you do have questions, I would invite everyone to use that Q&A tab. Unfortunately, we're not able to answer questions via the chat or raise hand. So please do use the Q&A. One question you may be able to answer, Alexei, is would EVPN, as discussed and demoed, be interoperable with other vendors?
Yes, the EVPN standard is has been defined by multiple vendors, and we've tested that. We've tested the interoperability during some Interrupt Fest as well. But the standard is interoperable. BGP by definition is also interoperable. And what I've illustrated here, whether it's root type 2, the multi-tenancy aspect, the root type 5 for L3 VPN, so both the L2, the ELAN service, and the L3 VPN will be interoperable, meaning you could have in this design, whether it's a leaf or a spine, you can have multiple vendor interoperating together as long as they follow the standard, and that has been tested as well. Sometimes standard can be up to interpretation, but that's a fairly robust technology now that's been tested and driven by many customers. So the answer is yes. So for the purpose of this demo, I've just shown everything was already configured. And what I suggest is, if some people are interested in looking at how to configure it, that could be a twice longer demo. But we could do some additional demo where we do the configuration itself in another session. So for the purpose of continuing and covering everything intended, I just want to go through, going back to the presentation. This is a summary of what we've seen. We've seen the IMET distributing the interest in receiving bump traffic on a specific layer 2 segment, VNI, so that leaf 3 did send the bump traffic to leaf 1 when the host 1 wanted to send an ARP request. This was sent to leaf 3 correctly. Then how the MAC address was populated, then the root type 2 generated, and how that was distributed to leaf 3 to provide complete end-to-end control plane and data plane reachability. I've discussed about many of these aspects here, the root types, and I think that was the purpose of the demo to explain everything and how things work, from data plane learning for the local MAC learning to control plane establishment and end-to-end data plane forwarding. Because we've already covered it through the demo, I just wanted to highlight. I think there was a question on different types, and one of the use case for additional route types is, for example, multicast. Multicast is developed also for EVPN. So EVPN supports multicast, both the layer 2 multicast and also layer 3 multicast, meaning you can have multicast as a transport for multicast overlay in your network, multicast VPNs. We're now going to see some design options, and one of them, when you consider the segmentation, is to provide a solution per tenant. The routing model we've discussed in the demonstration illustrated that the host was reaching its default gateway to route to remote destination, which was all layer 3. But what if there is some layer 2? What if we do have some VXLAN bridging, illustrated here, for example, between this this host, and there might be some layer 2 traffic going within the VLAN 10 that's stretched, and there's extension through the VXLAN VNI 1002. But when a host, here my host blue 10, wants to reach something that's behind another VLAN, there needs to be routing and bridging capability, so both integrated together, routing and bridging. This is the acronym IRB. There are different models for routing. In this instance, I've got all my VLANs everywhere, so that when the switch receives the traffic from the host, it's got both subnets directly connected. So in its routing table, it always has knowledge about where the other subnet is. So it can do a local routing to the relevant SVI, and then when it's inside, it has been routed to the SVI, then it's just bridging. It's in VLAN 11. VLAN 11 is bridging to wherever the remote MAC address is. We're now talking about bridging, right? Just layer 2. So one of the concerns with that design model for a tenant that has got multiple layer 2 segments and multiple subnets, multiple SVIs, multiple different gateways, is that you need to have those VLANs and those layer 3 interfaces everywhere. So if a tenant has got 100 of them, you must have those 100 VLANs everywhere. So it doesn't scale, but it is supported and typically used for interoperability purpose. Another model where I want to be more efficient, I would want to have my VLANs only where I need to for a given tenant. And that means I've got, for example, on leaf 1, I've got my VLAN 1011. This device here might have all of them, but I might have only my VLAN 12 on the right-hand side. So how do I provide reachability? Because now when a host sends traffic to the switch, to the default gateway, that routing table, as illustrated here, might not have the subnet for the VLAN 12. So it can't reach, it doesn't know the destination. One of the solution to that is ideal, I think, for multi-tenancy. It's the symmetric IRB, which means we allow the routing information to be distributed across the different PEs or VTEPs through an IPv4 or L3 VPN. So that's combining both the L2 VPN and the L3 VPN. The L2 VPN provides the L2 reachability, and the L3 VPN provides the prefix, the IP address information, the subnet information with the route type 5 is going to provide the routing information needed to reach the subnets that are not locally present on the original VTEP, on the VTEP at the origin. Let's take back the example we had before. We've got a host 1 here in VLAN 10, and it needs to reach a subnet in VLAN 12. That's here. So the L3 VPN that we've seen is going to distribute these subnets. I've got the subnet orange here. That's going to be distributed by L3 VPN to my remote PEs. So now my leaf 1 here, that VTEP, will have that prefix, will have that routing entry, and will therefore be able to route to that remote VLAN 12. So it provides a much more efficient way of routing and is ideal for multi-tenancy. Another, we're going to keep developing on design options and use cases, but I'd like to pass over to Sean for discussing the additional details.
Thank you, Alexi, and welcome to the virtual Arista office. So thank you, Alexi. So I think you've covered off a lot of the detail there about the design, and now we're going to talk about some other design options that we have as well around host access and around ARP suppression. So there are traditionally, a few different multi-homing options out there, and something that you probably have seen before is the use of MLAG or the like. So effectively, this is your kind of traditional two peers or two top of rack devices with a kind of peer link between the two. It might have a different name for other implementations, but we call it a peer link. So kind of a redundant link between the two. And the idea of this is to provide a redundant connection to the end hosts that might be connected, or it could even be an end device, a networking device, a router, firewall, whatever it might be. I would say, MLAG is well proven, it's widely deployed, and Alexi has already been demonstrating some of that working in conjunction with EVPN. It's relatively easy to configure, and you can use, relatively low cost twin-ax cables for these peer link connections. But in addition to this, it is also possible to leverage EVPN to provide active-active multi-homing at top of rack. So using the protocol itself, we could actually remove the link, remove the peer link between the two, and then actually expand beyond two peers. So rather than just the two peers that we're limited to with MLAG, we can grow beyond 2 to 3 or even 4 top of rack or edge devices for active-active multi-homing. So a quick look at MLAG and how it works. I'm sure many are familiar with MLAG or the like. But effectively, we have two VTEPs or two tunnel endpoints, which have a peer link between the two. We then connect our end server or end host or end networking device. And then traffic can be sent via a shared port channel to either of these. And then either of the VTEPs or the tunnel endpoints can pick up the traffic. It can encapsulate it into VXLAN, into MPLS, and send it across the layer 3 backbone, or we could use it in conjunction with layer 3 EVPN for routing between subnets, or with integrated routing and bridging to do both of the above. When we look at active-active multi-homing, it's a bit different. So we're actually leveraging the routing or leveraging EVPN to provide this host redundancy. So multi-homing uses the concept of a shared segment, or otherwise known as an Ethernet segment identifier or an ESI. Now note the ESI isn't a VNI ID number. It's a separate identifier number which is used to ID that shared segment. Think of this as kind of a lag group or a port channel group. So it's an ID number which specifies which devices are sharing a port channel down to another device. The ESI is again the shared ID which is used on 2 or more PEs, and then the VTEPs themselves, the tunnel endpoints themselves within EVPN, they discover one another via what we call a type 1 EVPN route that I will cover in a second. In multi-home deployments, of course, these two devices are sharing a single Ethernet segment. So when it comes to broadcast unknown unicast or multicast traffic, otherwise known as BUM traffic, we do not want there to be any duplication of traffic onto the shared segment. That would be a bad thing, right? So in order to deal with this problem, EVPN as a type 4 route that is able to elect a designated router or a DR for forwarding traffic onto that particular segment. Now, type 4 routes, these are advertised only by PEs or tunnel endpoints which are participating in the shared ESI. Once these have been, and they're only picked up by other PEs which are participating in the ESI. So once a PE, or once these route types have been received, this allows them to elect a DR, a designated router, which ends up being the lowest IP address. And then the lowest IP VTEP or tunnel endpoint is then the designated router that is the only one allowed to forward broadcast, unknown unicast, and multicast traffic onto that particular segment. Now, once we've worked out who's going to be the designated router, we also need to allow other tunnel endpoints within the domain. We need to let them know about the shared Ethernet segment. That's where a type 1 route comes in. So type 1 routes are advertised by any other devices participating in the ESI, and they are used for fast convergence or mass withdrawal of entries, but also they're used to allow traffic to be load balanced across the two devices which are forwarding traffic onto that particular segment. So when we have this set up, we do still have type 2s. So if you recall back to Alexi's presentation, we do have a type 2 routes being advertised, which will specify the MAC address and the MAC to IP binding. These are advertised by only one of the VTEPs which are participating in the shared segment. However, both or all of, I should say, all of the PEs which are participating in the shared segment would also send a type 1 update with its own IP address as the next hop. When a distant PE or a VTEP receives a type 1 update, it's able to add both of the VTEPs as the next hop for a MAC address and then load balance across both of the remote VTEPs. So if we look at this a bit visually, we have two PEs here participating in ESIA and ESIB. ESIA goes to server 1, ESIB goes to server 2. PE1 is .1, PE2 is .2. Both of these, one of these will advertise a type 2, and the type 2, rather than pointing to an IP address, it will point to an ESI ID. And this allows the remote VTEPs to realize that the server is part of a shared segment. It then has to wait, or the remote PE then has to wait for the type 1 routes to be received that specify the next hop IP of the remote PEs. So PE3 over here receives a type 1 from PE1 and will receive the type 1 from PE2. When it adds those entries into the MAC table, and in conjunction with the type 2, it's now able to load balance traffic on a per flow basis. So we're not doing, we're not doing a per packet forwarding or anything like this. It's a per flow basis. We're able to then share traffic across PE1 and PE2. Now, where this becomes important is failover. So when a PE loses connectivity to a shared segment, it can send out a withdrawal update, so a type 1 withdrawal update. So you can see here that PE1 has lost connectivity to server 2. So now it's saying, please withdraw ESIA via 111 via .1, and then the remote server can very, very quickly remove any MAC address which is associated with ESIA from its table. So it doesn't need to, it can just say ESIA has been removed, and therefore remove all of those MAC addresses very quickly from the MAC address table. Once we have our MLAG set up, or maybe our EVPN active-active multi-homing, how do servers or how do end hosts actually get to their gateway? So one solution we kind of have here is the ability to configure a virtual IP address across every top-of-rack device. So you can see here, these servers all use 10.1.1.254/24 as their default gateway. And this IP address is configured everywhere. By using the virtual IP, we are also not burning an IP address just to address the top of rack switches. Once this has been configured, we can then configure a shared loopback IP per pair of devices. So per pair, or if we're using active-active multi-homing, maybe for 3, maybe for 4, participating in the same domain, we advertise a shared loopback, and this is used as the next hop for the flood destination, so type 3 routes, which Alexi's already explained, and as the next hop IP for type 2 for MAC addresses and type 5 for IP prefixes. But the nice thing about this solution is its ability to configure the same gateway IP across every top of rack switch. Another added benefit, and I think Alexi showed a bit of this earlier on during his demo, was this ability to implement ARP suppression. So MAC to IP bindings are learned locally by a VTEP. It looks like the ARP table, right? So you have the MAC to IP binding, but what we can actually do is advertise this ARP information, the MAC to IP binding information, via a type 2 entry that other devices are then able to learn. This means that we can suppress ARPs across the infrastructure. We can suppress the broadcasting of ARP traffic, and we're not reliant on waiting for that learning to happen before remote devices can learn where other devices reside. And this is all done by ARP snooping or DHCP traffic on the VTEP. Once the remote device has learned about a MAC to IP binding, it is then able to perform effectively a proxy ARP response to ARP requests which are local. But most importantly, this type 2 entry, this MAC and IP type 2 entry, is advertised in addition to the MAC only type 2 entry, which means that if the MAC and IP route table is cleared or the ARP table is flushed, we still have the MAC entry available to get to that device. So I've spoken about a number of different options there from a design perspective. Now, how about actually applying this to a real life design or a multi-tenancy example? So first of all, multi-tenancy via network segmentation. Who uses it? Who tends to segment their network or provide these multi-tenancy setups? So service providers and hosting providers typically use this for customer separation, maybe for providing shared services to their clients, like DNS services to their clients. Typically, hosting providers might only need a layer 2 only service for connecting their tenant devices. So they could be, their tenants might bring in their own networking devices, they might bring in their own servers, and the hosting provider is just providing that kind of layer 2 wire service over the top. Enterprise customers typically using this to logically segment production, development, campus, non-prod, whatever it might be from one another. So fairly typical is for an enterprise customer to have maybe 4 to 5 different VRFs that they need to span. How do they do this today? They're usually doing this via layer 3 VPN services that might be provided by MPLS, or they might be doing it with VRF Lite, or today they might be physically separating their environments and probably not making best use of their assets. There's also the benefit of being able to apply security enforcement between environments by separating out these different environments like production, development, campus, etc. They might also be providing shared services as well between these different tenants. And finally, Web 2.0 or cloud customers are using network segmentation, of course, to get best use out of their physical assets, again, for customer separation, or it might even be for separating their own microservices or their own applications from one another. So using Arista for multi-tenancy and some of the advantages there that we offer, and there's obviously the ability to logically segment up the shared infrastructure and make best use of the physical assets across most of, or if not all of, the hardware now. There's a tenant IRB options which are there as well, so tenant integrated routing and bridging across all of those platforms. Quite a degree of design options there as well. So I've already spoken about the ability to use MLAG or multi-homing active-active. We've already spoken about the ability to use asymmetric or symmetric IRB. And all of these are proven in multi-vendor setups. So every year we participate, as well as other vendors, in the EAN-TC testing. So if you go to our website, you can find a link, or via their website, you can find a link to the 2019 results, and the 2020 results are being worked on right now. You should see that soon. As Alexi has shown very well, I'm sure, as you've seen in the demonstration, there is a rich troubleshooting output, lots of show commands that you can run, very easy to work out what's going on and where, and very easy to troubleshoot if there's any issues with a particular setup. And as I mentioned, a wide choice of hardware as well, right? So one thing to note is that now EVPN and VXLAN is very much supported on our campus PoE devices. So you could bring this separation, or bring this segmentation right into the campus and be able to separate maybe different campus environments from one another. One kind of practical use case, or one nice use case of EVPN is this ability to do data plane segmentation end to end. So you could use EVPN with VXLAN or MPLS to provide campus segmentation, on-premise DC segmentation, WAN, or even within the public cloud, using maybe the virtual EOS solution that we provide as well. So you could have the same separation from different environments through every network within your environment. And by leveraging the likes of, you've probably heard it before, Cloud Vision Portal, we provide seamless provisioning across all of these environments, auto deployment and update, of course on a standardized configuration across the board, with multiple monitoring options in there as well. But I think what's most important about EVPN here is the fact that it's a standard-based segmentation that you can apply to any environment and interop with most other vendors as well. One other kind of practical use case is around campus. As I've mentioned, this ability to provide separate environments and separate these from one another across multiple different sites. So you might have multiple sites that have local PoE devices or local campus devices. You can use VXLAN within those environments to provide separation. And then between the environments, we can use IP or MPLS as a forwarding plane for connectivity between these environments as well. And again, it's open, interoperable, and very scalable too. So when thinking about these different environments and these different use cases, and who uses these different use cases, like service providers, like enterprises, or Web 2.0 or cloud type customers, there's always the question about how you would like to deploy this. Do you want to provide layer 2 connectivity, layer 3, or maybe combine the two? So for the layer 3, the layer 3 example, layer 3 EVPN example. So using layer 3 segmentation, Alexi's already explained a lot of how this works already, but there is the ability to advertise VRF-aware IP prefixes across multiple tenants, or across multiple tenants, and keeping them separate. And then VXLAN is able to provide that layer 3 connectivity, but without the layer 2 connectivity. So really, this is kind of this is very similar to what you might see today with a VRF Lite solution, or with a RFC 4364 or VPN v4 MPLS type deployment. It's just that when you do this on VRF Lite, multiple BGP sessions have to be set up. It can be quite unwieldy and quite difficult to manage. And then if you're looking at RFC 4364 or VPN v4, typically you would have to use more expensive MPLS routing type devices to provide that separation. The beauty of EVPN, and kind of one of the advantages of EVPN running over VXLAN, is the fact that you can do this on regular switches. You can do this on regular DC switches, and you can do it on even on the campus devices, which I've already mentioned. So PoE, bringing it right down to the edge of the network and providing EVPN and separation. When we look at just a kind of a recap of how this looks visually, again, as I've mentioned, IP subnets using layer 3 EVPN, the segmentation is happening on a subnet level. So this is being brought down to the top of rack, and the different VRFs are brought down to top of rack. And then the VRF awareness is then added to this via EVPN. VXLAN is actually used then to provide that overlay transport between the VTEPs. And then the VXLAN network identifier is associating the VRF with the VRF with the overlay, or with the VTEPs that are that the traffic is being transported between. From a configuration standpoint, I think again Alexi's explained a bit of this already. When you set up the EVPN sessions, these are created from the VTEP or from the top of rack switch to the spine, or even to the campus core. The campus core or spine devices then act as a root server and then share the type 5. So these are the EVPN type 5 routes from one top of rack device to another. Once these have been shared, it means that the local VTEPs can import these routes into their VRF, and then local devices have then routed or reachability via the routing table to one another over the shared infrastructure. This example here, we have VRF green, VRF blue. This could be a production environment. This could be a non-prod environment. It could be other overlapping address spaces. So you might have overlapping IP address ranges that you want to deploy. This allows you to do that too. The other kind of use case is just for layer 2, right? So you could use EVPN purely for providing layer 2 connectivity to end ports across an environment. And all we're doing here is stretching VLANs across these switches. And again, this is very, more popular, I'd say, within kind of a hosting provider environment, or maybe even a service provider environment, where they do not want to get involved with customer routing. They just want to provide connectivity. All we're doing here is advertising MAC addresses using type 2 routes. EVPN is then used to dynamically discover the remote VTEP, so it's advertising who is connected to a particular layer 2 segment. And then, of course, advertising the MAC addresses between the VTEPs to provide connectivity. VXLAN, of course, is then used as the forwarding plane. This is kind of similar to an ELAN or a VPLS type of service. Again, how does this look from an actual configuration standpoint, or more from a design standpoint? Again, in the same way as the layer 3 setup, the BGP sessions are set up from leaf to spine, or from leaf to core. You might want to call it a campus core. And then the EVPN routes, the type 2 routes, are then used for advertising the MAC bindings between the devices. But of course, how do you route between these different segments, or these different layer 2 domains? That's where typically a customer would use an external gateway or an external router for routing between these layer 2 segments. So you can deploy, another router for providing this, or you could add another VTEP here that maybe is the EVPN aware to provide the routing between them. Then finally, we can combine all of this if we want to, and this is fairly, this seems to be the most typical deployment scenario today, is combining layer 2 with layer 3 and using what we call integrated routing and bridging. So integrated routing and bridging allows us to stretch the IPVRFs using the type 5 routes. It allows us to stretch VLANs using the type 2 MAC entries. And as mentioned, we're able to advertise this MAC to IP binding using a type 2 MAC IP route. So we can gain ARP suppression, and we can gain this. We can leverage the control plane for MAC learning. As mentioned, there's 2 different models for for IRB. There's the symmetric IRB or the asymmetric IRB. We support both. You can use both of these models. You could even use us as the gateway between the two. So if you have an asymmetric setup and a symmetric setup, you can actually bridge that gap with or kind of stitch these two environments together using one device or a number of devices. So we support both, but I would definitely say that symmetric IRB is the recommended approach. Is probably the most popular approach, and the one that we kind of assume here. Again, how does this look from a design perspective? Again, the BGP sessions are set up from leaf to spine or leaf to campus core. EVPN is then advertised in the type 2 and the type 5 routes via multi-protocol BGP. And then, as I mentioned a little while ago, we then configure each leaf to act as an anycast gateway, which then allows us to stretch layer 2. So we have this green VLAN being stretched, the blue VLAN being stretched, and then the gray could be unique to that pair, and the turquoise could be unique to another pair. But in addition to stretching these layer 2 domains, we actually provide the ability to then route between them as well. So routing actually happens directly at the top of rack switch. So the routing will happen closest to the endpoint from where the traffic is coming from, and then it can send it to the destination BTEP if it needs to as well. Of course, this is just what an internal environment, right? How do you transit out of the network? So typically, you might see the term a border leaf. So a border leaf is able to provide transit out of the network, or you could be adding services. So, and I'll come into this in a second. So you add different services on what we might call a services leaf pair. So, as for external connectivity, how do you get to the WAN? How do you get to the outside world? How do you get to the internet? This is typically where we would have a border leaf pair where external routers could be connected or external connectivity could be added. The way that these are connected, they can peer within the tenant VRF. We then take the routes that are advertised to us from the external router. These will then appear as type 5 IP prefix EVPN routes, and then advertise to all the other leaf switches which are participating within that tenant. So now traffic from leaf 11 and leaf 12, they have connectivity, or they have a route to the outside world via leaf 21 and leaf 22, and they're able to load balance that traffic between the two and reach the outside world. So this is a fairly typical setup. Shared services. So how do you connect the likes of load balancers, firewalls, or any other network appliance? The leaf and spine type designs that we're talking about here don't have a natural bottleneck. They don't have a natural bottleneck in the network like you would with a core distribution or access type design. There's no kind of natural place where traffic is actually flowing through. So what we do here is that we can add services on a services leaf and then advertise routes to these from the services leaf in the same way that we do for external connectivity, and then draw traffic towards them across the VXLAN or the leaf and spine infrastructure. So once we add our maybe a load balancer over here, and we advertise a route to that, devices which then need to get to that load balancer, or that VIP as it might be, would then see a route via a type 5. So a type 5 entry is advertised to leaf 11. Leaf 11 then has a route to the services switch, and then can reach the load balancer. One example of this is firewalling, right? So how do we provide secure segmentation of tenants? So in the same way that we place the external routers, or in the same way that we place maybe a load balancer, we can place a firewall at the services edge, or maybe the border leaf, and then have maybe one interface or one virtual interface inside one tenant, and the other interface in another tenant. And then the firewall itself can provide the routing between the two, and of course the security policies that need to be applied between the different environments. This is a very, it's a very common scenario that we see users setting up, and they use this for providing connectivity between different environments. It might be between prod, pre-prod, development, etc. Is by having this kind of edge firewall solution. So just to summarize, lots of design options. There's obviously the option of layer 3 only EVPN, layer 2 EVPN, and then combining the two, which is the most common, with integrated routing and bridging. Using this, there's the ability to logically segment your environment, your physical environment, and make best use of the assets. And just bear in mind that this can be done on pretty much every device that we have now, every platform that we have. Secure separation could be provided via external firewalls using kind of a services leaf or a border leaf. And then the beauty of symmetric IRB, which is kind of the assumed design approach today, means that we can reduce configuration by only configuring VLANs where we need them. We can provide ARP suppression, so leveraging the EVPN control plane for advertising MAC to IP bindings, and then also avoid some of the VNI scaling issues, as we only use VNIs where we need them. But of course, this is all kind of local to a data center or local to a campus. How do we provide this segmentation end to end using EVPN? And that's where we start to talk about data center interconnect. We start to talk about the WAN, and maybe where we would like to use MPLS as the forwarding plane between these. And I'll start to talk about this in a second. But David, do we have any questions at all out there?
Thank you, Sean. Yes, we have a number of questions, which we're doing our best to answer most of them in the Q&A text chat right now.
Yeah.
One we do have for you, Sean, is today I have a flat layer 2 network. Should I use EVPN with VXLAN?
Good question. I guess it depends on scale as well, right? I think if it's a small flat layer 2 type network, and I'm assuming you have something like MLAG set up as your gateway, and maybe layer 2 top of rack switches, that might work. But I think as networks start to scale and we start to see this explosion of entries and MAC addresses and state, it might be worth considering deploying EVPN to provide that, maybe the same functionality, maybe just providing layer 2 connectivity. But it is possible now to use what might traditionally be seen as basic top of rack switches. They can run VXLAN, they can run layer 3. They can leverage EVPN to reduce that state within the network or the huge broadcast domains, and then forward traffic over a stable layer 3 underlay. I hope that answered that. So, as I mentioned, VXLAN or MPLS. So, we've been talking very much, and I think as you've probably seen, we've been talking a lot about VXLAN, right? The ability to run segmentation over an IP infrastructure. It works, it's simple, it works very well. It works very well in a data center or even in a campus. But why would we need to use MPLS? MPLS is something that we've probably seen more in the WAN, in data center interconnect, where customers want to preserve segmentation, but they want to achieve features like traffic engineering, protection of services or protection of paths, rapid convergence in a failure situation, end-to-end circuit monitoring, or QoS mappings. Now, for those of you out there who operate MPLS networks, I'm sure these are services that you're familiar with that you might want to leverage with EVPN. And at this point, it's worth noting that EVPN has always supported multiple different encapsulation protocols. VXLAN, as we've spoken about already, but also MPLS. And it's worth noting that MPLS as a forwarding plane is supported on our devices using the 7280R or the 7500R platform. Of course, EVPN is providing the VPN forwarding plane, right? The VPN labels for, or the VPN distribution, sorry, over MPLS. But of course, you need some way of transporting this traffic, and that's where an MPLS transport label distribution protocol is needed. So, who uses MPLS today and why? It's been around a long time, right? Protocol neutral, you can put any encapsulation over the top of it. It wasn't originally designed just for putting IP over the top. It's when we had lots of different protocols that we wanted to be able to encapsulate in a neutral encapsulation. And I think over the years, engineers have seen the benefits of this and they want to carry on using it. And of course, there are lots of different advantages to using it as well, including traffic engineering and fast reroute. So, service providers, this is very popular at service providers who use it for providing different services, for layer 3 services, layer 2, or VPLS. They might very well want to use it for traffic engineering, for making sure that particular paths are taken in particular scenarios, or maybe to avoid particular nodes in particular scenarios. And of course, for fast reroutes, for making sure that if there's a failure in the network, we're able to very quickly fail over to a backup link. Backbone and WAN networks, of course, you see this within these type of networks. And then for the carrier, the carrier kind of the RAN MAN type networks as well. Web 2.0, or the cloud providers out there. Again, very similar to a service provider. They want to use traffic engineering. They want to do auto bandwidth reservation. And of course, in their inter-DC backbone networks, which a lot of the time are just as big as the service provider networks, right? And then enterprise users as well. So enterprise users traditionally have used MPLS within their WAN for layer 3 VPNs. So being able to have isolation or segmentation between different layer 3 tenants. And then for layer 2 VPN, so providing layer 2 stretch across maybe their data centers. So, there's a lot of use cases there today, and customers that still want to be able to leverage these features, but with VXLAN, it might be a bit difficult. So especially around traffic engineering is not so well suited to pure IP. Fast reroute capabilities, you could argue that yes, you can reconverge very quickly, but there's not so much of an ability to set up paths ready to go within SLAs that might be set. So when we look at the kind of the full MPLS protocol suite, there's lots of obviously different services that we've already spoken about, different monitoring solutions that we've already spoken about. But of course, we do need some form of label distribution protocol or signaling protocols to allow maybe traffic engineering to happen. So what you might be surprised about, many on the call, is that Arista do actually support many of these, if not, well, pretty much all of these today. So, we're a data center switching company, but we do support LDP. We do support RSVPTE to a certain degree, using as a P node, I would say. We do support ISIS segment routing, and we support BGP labeled unicast. So labeled unicast allows us to program paths within the network. And then on top of this, from a traffic engineering perspective, there's ISIS traffic engineering, segment routing, traffic engineering, and constraint-based SPF as well. So yeah, you might be surprised, right? But we do support some of these, what might be considered service provider type features already on our 7280 and the 7500R platforms that we ship today. So, lots of different protocols there. Leverage them today if you want to. But if we're talking, and I'm going to give a very brief introduction to segment routing, how it works, some of the concepts, and where it might apply. But this is very much an overview, right? I think this is something that we would like to pick up again on a future webinar, and something that we'd like to deep dive into probably at a later date. But what is segment routing? You've probably heard a bit about it. The basic philosophy of segment routing is about simplification, right? It's its ability to reuse the IGP, so reuse ISIS or OSPF, or BGP and BGP to distribute labels, right? It reduces the number of protocols used. So you could actually use segment routing as a replacement for LDP. So rather than having an IGP running, say OSPF or ISIS, and then having LDP running next to it, you can actually combine this and use the IGP itself to distribute the labels for MPLS. It means that, of course, we simplify the network by reducing additional signaling protocols, and we remove the amount of state that we see throughout the network, or maybe the amount of state we see through setting up full meshes of tunnels for RSVP. Segment routing natively supports ECMP. So where we see an abundance of links within networks today, rather than just using a single non-ECMP path, segment routing allows us to natively make use of all the links available, rather than RSVP and this kind of single path that we have. We also have the ability to encode the path into the label stack itself, so we can perform source routing. If anybody remembers source routing, we can do this today and actually have the path of traffic encoded into the data plane, which means that we could offload the traffic engineering to an external controller that can do the heavy lifting. That can do the external controller can do the traffic engineering and work out the particular path that we want to take and encode that into the forwarding plane. So a few concepts of segment routing. We have segment routing kind of looks at or envisions the whole network as a collection of topological subpaths called segments. So what I mean here is that each part of the network, whether that's a node, whether that's a link, whether that's a collection of nodes using an anycast kind of view, segment routing will break the network down into these different components, and then is able to actually advertise them, because it is the IGP. It's able to advertise the entire topology to an external controller if you want to do traffic engineering. So again, you don't have to do traffic engineering, but you have this ability to. Once we've done this, we have this concept of a global label and a local label, and then the packet is transmitted with a list of segment IDs that will specify the path through the network. In terms of application, and saying it again, it's very important to note that you do not have to do traffic engineering, right? You can use this to remove LDP and just follow the IGP, the IGP path, the shortest path through the network using the IGP, without adding an additional protocol or additional complexity within the environment. But of course, you could use it as a traffic engineering alternative using an external controller. So it's kind of one of the challenges here is that you do need an external controller for programming a traffic engineered path, but it means that you could develop your own. You could use one off the shelf. We have some examples as well, and I would definitely recommend that you look for, have a look at this MPLS segment routing white paper that we published that explains a lot of these terms and how it works. Apologies for the rather long link, but it's fairly easy to find. So again, just a quick overview of how segment routing breaks down the network. It divides the various nodes into what we call into a node segment, and then we divide the links into a link segment. So link segment or link segments are locally significant, and then the node segments are globally significant. Once you think about the fact that these node IDs are globally significant, it means that you can then encode that into the traffic, right? So if I want traffic in this, the shortest path here would go node 1, 2, 5, and 6. And if we were deploying this as a replacement for LDP, that's the path it would take, right? It would take the shortest path through the network. But what segment routing allows us to do is actually encode a particular path into the header of the traffic. So if we wanted all traffic to go via node 3 or node SID 3, we could add that label to the packet header, which would mean that traffic would go the shortest path to node 3, so go 1, 2, 3, and then take the path to node 6. So of course, I might have to put in node 4 as well. So we go 1, 2, 3, 4, 5, and 6, and we're able to actually encode that into the packet header. So how are we actually, how does it actually advertise the ID numbers? So as I mentioned already, the ID numbers are well, segment routing is the IGP, right? Segment routing is part of ISIS and part of OSPF, which means that the ID numbers or the segment IDs are actually advertised as TLV extensions to the IGP, to OSPF or ISIS. And this are then, like I've said already, this allows us to program in these different entries or maybe traffic engineering. So one other kind of analogy of I guess more segment routing traffic engineering is that after we've advertised the full topology, because we're using a link state protocol here, either ISIS or OSPF, we're advertising that to an external controller. The external controller could then specify a number of constraints to get from one node or from one place to another. So in this analogy here, we're trying to work out how we get from our corporate HQ to the airport, and then we're trying to work out the path between the two. One of the constraints that we've put in would be to avoid highways. So maybe avoid what you call, I guess, a low latency link, right? So we could have a similar constraint programmed into the controller. So we could tell the controller we want to avoid the highway, we want to avoid the low latency path and take the higher bandwidth, the lesser cost path. Once we've then computed the path, we're then left with the computed path that we want to take. Applying this to segment routing, we then take one of these paths and we then have the different kind of directions that we need to take. Each one of these directions would be the ID number, which is programmed into the header of the traffic and ensures that we take this particular path. So now the traffic is able to take that path through the network. So finally, just to and this has been a very, very brief overview of segment routing, but I think it's worth us mentioning the advantages of it and what it can give you, and really how does it help. So in my opinion, it kind of takes the best of LDP, the best of RSVPTE, and provides it as a single protocol, right? So we gain simplicity from an operation perspective, because it's easy to deploy, easy to extend in the IGP. We're not specifying a separate label distribution protocol. We're using the IGP. The IGP is already there. OSPF or ISIS is already configured. It's already there, and we're leveraging that to distribute the labels. Label allocation is global. So this is quite important. When your label allocation becomes global, it means that we can then compute paths outside of the network. We can compute paths by using a controller, and the controller, which has probably much more flexibility, it's not part of your network. You can have it there ready to calculate a path and program the path within the network. We have native ECMP, native ability to use multiple paths in the network, and also support for traffic engineering. Once we've removed all of the state within the network itself, the traffic engineering scale becomes huge, because we're taking that state out of the network and we're then programming it into the header of the forwarding plane, and we're not having to keep the state within the network itself. The state is retained within the controller. One point I've not mentioned here quite so much is also fast reroute is provided via traffic or TI-LFI, so traffic independent loop free alternative. And what this provides is fast reroute capability with 100% coverage. And again, we're probably going a bit deep here, but we can explain this on a future session. It also supports natively IP version 6. So without any extensions to segment routing, we have support for IP version 6 and IP version 4. Just one, I guess one drawback here is the limited support of multicast, but there's no reason why you cannot run multicast in parallel to segment routing. At the same time, it's worth noting that you can run segment routing in parallel to LDP. You can run it in parallel to RSVPTE. You don't have to. It's not an all or nothing setup. You can run all of these protocols side by side today on our devices, and then maybe move services from maybe kind of a brownfield setup, an existing setup, over to segment routing when you're ready and when you see fit. And the last point I'm going to make is this fact that segment routing doesn't have to be used for traffic engineering. Segment routing can be used in place of LDP. So you can use it for your regular label distribution and actually have that in place of an additional protocol and leverage the existing IGP. So how does this link back to what we've been talking about with EVPN segmentation? This provides that kind of last hop, as it were, between different networks, and it allows you to retain that segmentation from one environment to another. So you might have different campus sites, you might have different data centers with different VRFs and different tenants configured. By using MPLS in the WAN or within your DCI, you can retain that segmentation and also leverage all of these benefits here by using segment routing. Or, like I said, you can use RSVPTE, you can use LDP, but segment routing seems to be the way that many people are going nowadays. So just to finish up, I'll hand back over to David. David, is any more questions before you conclude?
We just have one question for you in relation to MPLS. We have somebody asking, would you prefer to use MPLS in the data center over VXLAN?
It's possible. You could use it. So the 7280R platform, the Jericho-based platforms that we have, as I mentioned, they do support MPLS today. You could use them. There's no reason why you couldn't have MPLS all the way down into the data center. It's just that the lower cost, the more I guess the more regular data center switches and the campus switches only support VXLAN. But yeah, there's no reason why you wouldn't. Why you couldn't? I'd say. But from a troubleshooting perspective, from an operational perspective, VXLAN is easy, right? It's IP. It's very easy to work out what's going on. It's very easy to understand. Whereas MPLS might, you might very well have the skill set out there to do it. But MPLS, maybe a bit more difficult to manage, maybe a bit more difficult to administer. But it could be done. But I would say, use VXLAN within your data center, use VXLAN within the campus, connect everything together with MPLS, and leverage some of the features that we have there for moving between the two, kind of that gateway between VXLAN and MPLS, and translating between the two. So I hope that helps.
Great answer. Thank you very much, Sean.
Thank you all.
So in conclusion, if we take a look at the next slide, really just to summarize what we've been covering today. By now, hopefully you've seen an overview of how EVPN provides segmentation. That should enable you to have an efficient, scalable, and secure division of that physical infrastructure, whether you're using layer 2 or layer 3 VPNs, or perhaps a combination of the both. You can also look at segment routing. We've looked at multi-tenancy and some design examples of that. And I think one thing I'd like to stress is this is available to deploy today. We're working with customers who are deploying this in anger in production deployments. And I think it's a really exciting time for this technology. So I think one question we're seeing a lot is, how do we take this forward? How can we follow up with this? Now, one example I would suggest is we have a number of design guides, design and deployment guides on our website, arista.com. And so if you just Google for Arista design guides, you should get that URL. Naturally, if you want anything that's in more detail, hands-on, assistance, configuration, and so on, your Arista systems engineer will be the preferred place for that. And I have just been told that we are planning some further webinars on EVPN. So if you enjoyed this webinar, we have a number of EVPN specific webinars that are coming up shortly. The first of which I believe is planned on the 9th of April, which is a Thursday, looking at EVPN active. And there are some further EVPN webinars looking at EVPN with multicast, EVPN with Ansible. What I would recommend for those is if you're subscribed to our email marketing list, you should be getting an email in the future with details of that webinar. If you're not on that email list, if you simply Google Arista webinars, you should get the first result on Google detailing all of the webinars we have planned. Now, in addition to the EVPN webinars, some of you, particularly if you're in the EMEA region, might be familiar with our Cloud Builders events. Now, as you can imagine, there are some challenges with the current situation of having in-person Cloud Builders events. And so we'll be having a number of exciting webinars to really take that Cloud Builders content and make it virtual. So again, do look out for your emails on this. We will be doing a mail shot once we have confirmed these sessions. But these six sessions here are covering the virtual Cloud Builders events. So we'll be looking at cloud vision, software innovations, edge routing, cognitive campus, next generation visibility and analytics, and looking at the continuous innovation of the data center. So do keep an eye out for those webinars. We'll be contacting you shortly with details of them. So with that, all that is left is to wrap up. Thank you very much for your time. Really hope this was informative, and enjoy the rest of your day. Thank you very much.